Good morning, students. Now we are going to conclude our chapter on energetics. The third topic of this chapter is about the enthalpy change and bond energy. We've discussed what enthalpy is previously. We can think of enthalpy being the chemical energy or energy that is possessed by an object due to their chemical structures. Now, what is bond energy then? Okay. Now, we're going to define bond energy as energy that's going to be required to break 1 mole of covalent bond. It has been found that every type of covalent bond, they require a certain amount of energy. For example, a single bond, hydrogen to hydrogen, they may require, let's say, about 75 kilojoule per mole. Or oxygen, double bond to oxygen, they may require, let's say, 215 kilojoule per mole. Or similar. Okay. The idea is this. Whenever we break a bond that's already present, we need energy. Hence, by definition, bond energy will be a positive value. It's a requirement. Now, on the other hand, the same amount of energy will also be released if we make the bond. If we are going to break 1 mole of hydrogen to hydrogen, making, let's say, from hydrogen and hydrogen goes into 2 independent hydrogen, we are going to require 75 kilojoule per 1 mole. It follows that whenever we have 2 free individual atom of hydrogen, we make the bonding into hydrogen to hydrogen single covalent bond, then we are going to release the same amount. This is going to be exactly the same amount that we require, in order to break them. So the same value that we need to break something is the same value we are going to release when we are going to make them. By the way, it's important to understand that bonds are broken in a single way, in a single step. So, like example, double bond of oxygen, they go directly into oxygen individual atoms. They do not break into, let's say, oxygen double bond oxygen goes into oxygen single bond oxygen. Nope, doesn't work that way. They work into directly bonded. Hence, breaking 1 mole of double bond oxygen is not the same with breaking 2 bonds of single oxygen. So bonding this is not the same with breaking double bond of oxygen. This is the general rule, happens for any type of multiple bondings. So nitrogen, triple bonding to nitrogen, is not the same with 3 nitrogen single bonding to nitrogen. There are different type of bonds, hence the energy is different. Now, how about the enthalpy change during a chemical reaction? We start with the simple idea that chemical reaction, they are rearrangement of atoms. So how can we arrange atoms? Generally, atoms will have a maximum amount of bond that they can make. So to rearrangement, we need two steps. First, we're going to break old bonds. And the second, we're going to make new bonds. This is the general concept of how reaction starts. Example. We have two hydrogen react with oxygen to make two water. Two hydrogen means you have hydrogen, single bond to hydrogen, twice of them. And oxygen is double bond oxygen. We're going to make water molecule, which is an oxygen bonded with two hydrogen each. Now, these reactions is actually happen in two steps. The first is we cut these bonds. After cutting those bonds here, what we have will be free individual 4 hydrogen atoms and 2 oxygen atoms. Those atoms free to move, then they're going to make new bonds. So first, break bonds, then make bonds. In order to find out the enthalpy change accompanying these reactions, we will be given a list of bond energy. For example, we might be given like hydrogen to hydrogen, that's going to be, let's say, 75. Okay. Oxygen, double bond oxygen, let's say maybe, let's call them maybe 200 or something. Oxygen to hydrogen, maybe it's just, let's say, 115 or some such. The calculation of enthalpy change are two-step process. First, we're going to make a list of all the bonds that are being broken. Okay. We have here hydrogen to hydrogen and oxygen double bond to oxygen. Next, we found what's the number of them. We have 2 and oxygen only 1. We multiply by the energy. That's going to multiply by 75, multiply by 200. And the result is for a total of 350. So this 350 is the energy that we need initially. Okay. Previously, when we talk about the pathway diagram, from the reactant, our energy is going to increase by 350. And we have the transition. Is the reactant. We have 2 hydrogen plus oxygen. The transition here are 4 individual hydrogen and 2 individual oxygen. What happens next is we need to find out how many bonds that was made, the number of them, how many, and the energy for that type of bond. We multiply, we get total. So there's only one type of bond that is made them here. That is oxygen to hydrogen. O to H and H to O is the same. Okay? So what we have is just a single type of oxygen to hydrogen. There are 4 of them. Okay? Each of them have the energy of 115 for a total of 460. Now, this 460 is always negative, always going down. A total here. So the enthalpy change is going to be 350 minus 460. In this case, negative 110. Then the enthalpy change will be negative 110 per mole. It is the strength of this theory that let us predict the enthalpy change that will happen should we do some chemical reaction. So nowadays, it is possible for us to estimate what will be the enthalpy change before we are doing the actual reaction themselves. I repeat, in this case, we have discussed about the enthalpy change and the bond energy. Bond energy is the energy required to break 1 mole of bond. The number I gave here is just illustrative. It's not the real number, okay? But to give some idea how to work with it. Now, the bond energy, the energy that we require to break the bond, is exactly the same amount of energy we are going to release when we make 1 mole of the same bond. So, breaking and making 1 bond, they will be energy neutral. We need to note here that bonds are broken directly. So we don't break oxygen, first break into a single bond, and then break into individual oxygen. No. Oxygen double bond directly broken into 2 individual oxygen. And the strength or the bond energy of a double bond is not the same with twice energy of single bond. So we cannot assume, if we know the bond energy of oxygen double bond to oxygen, then oxygen single bond oxygen is half of that value. No, it doesn't work that way. Okay, now we're going to the calculation between enthalpy and bond energy. Because chemical reaction is arrangement of atoms, we can depict chemical reaction as a 2-step process. First, we're going to break we're going to break the old bonds, and then we're going to make new bonds. Classical example here is hydrogen and oxygen goes into water. Please make sure that the reaction is balanced first. Balanced chemical reaction is important for correct calculation. Okay, now in this case, all the reactants must be broken, so reactants becoming single individual atoms. We do this generally by making some kind of table. We are going to find what are the bonds that's being broken. Okay. We are going to calculate how many numbers are there, the amount of each types, and look at the table that will be given, the bond energy of each types. That is why it's important to be able to make the line diagram in calculation of the bond enthalpy change. Afterwards, okay, we're going, the total of that is the energy that we need to go up into the transition condition. Always going up. At the transition condition here, what we have are individual atoms, not molecules. Atoms are then able, they are free to join into molecules using a new bonds. In this case, just oxygen to hydrogen. Oxygen, hydrogen, hydrogen, oxygen, they are the same. Order doesn't matter. 4 of them, 115 for a total of 460. Now, when we make bonds, energy is going down. Okay? So this is going to be a going down of 460. The net total is broken minus made electron. In this case, it's negative value. So this is an exothermic reaction. That's a little bit for today. Thank you very much.